Usually in statistics courses, we start with a statistical model. You know, like let x1 through xn be independent and identically distributed random variables from such and such a distribution with parameter theta, and so on. And then we work out all the technical details, living in the pure world of the model. And actual application of such models is often sort of like buying clothes at Walmart. You know, you try it on a few until one more or less fits, and then you buy it. The zipper example shows how if you are really honest about the model and you try to think about it seriously, you can find yourself facing problems that are not mentioned in the average statistics course. We'll start out with a little background preparation, then I'll introduce the example itself. The standard model for this example will be inadequate. We'll be honest, come up with a better model, and run into terrible problems related to the issue of parameter identifiability, a concept that you might not have encountered before. And then we'll see how maximum likelihood fails in this instance. And actually there's a 0.6, which is not listed here, in which there's a happy ending, but I did not put that in the table of contents. So as preparation, I want to talk about indicator functions and use conditional expected value to develop the law of total probability. So the indicator function for a set A is denoted like this. The indicator of A, it's a function of x, it depends on the set A, is equal to 1 if x is in A and 0 if x is not in A. So it's a yes or no binary for whether x is in the set A or not. And x is often a real number, but it could be a vector. And this is sometimes written like this, indicator for x being in A for short. And if you use this well-known formula for the expected value of a function of a random variable, that is, instead of letting y equals g of x and then taking the expected value of y in the ordinary way by summing or integrating against the probability distribution of y, you can simply take the function g of x and sum or integrate that against the probability distribution of x. This is a big theorem called the change of variables formula. So using that, you have the expected value of the indicator function for the set A, which is just a g of x, right? Equal to the sum of the g of x against the probability of x. But what happens is that this indicator function is 0 when x is not in A, and that 0 is multiplied by the probability, so that this indicator function zeroes out all the probabilities corresponding to x values which are not in the set A. And so this expression here is just a sum over all the x in the set A of the probability of x, and that's the probability that x is in A. So that the expected value of an indicator is a probability. If x is continuous, you have pretty much the same thing. You have the formula for the expected value of g of x, the indicator of function for the set A of x, and that again, the indicator function multiplies the density by 0 for any x which is not in the set A, which essentially just takes those parts of the density function and erases them, leaving the area which is sitting over x values that are in the set A, and that again is just the probability that x is in A. And so in either case, we have that the expected value of an indicator is a probability. So this applies to conditional probabilities too. So that the expected value of the indicator of x given y, well, instead of just summing it against the probability distribution of x, we're summing it against the probability distribution of x given y. So it's the same, absolutely the same stuff goes through, except with conditional probability, which is a probability, instead of ordinary probability. Or if it's continuous, you've got exactly the same thing, but with density instead of a probability mass function. In either case, you get the conditional probability that x is in A given y. That is, the conditional expected value of an indicator is a conditional probability. Now, double expectation, we'll use this as follows. The double expectation says that the expected value of any random variable, including g of x, is the expected value of that random variable given of function of x given y, where the outer expected value, this outer expectation is carried out with respect to the distribution of y, whereas the inner expected value is carried out with respect to the conditional distribution of x given y. So we have exactly what you would expect, is that the expected value of the indicator function is just the single expected value, which is the probability x is in A. And so you can take this probability that x is in A and write the first part, right? This double expectation. But what's inside is just the conditional probability that x is in A given y. So for example, if y is continuous, you've got you basically take this conditional probability that x is in A given y, that's the conditional probability, and you're integrating it against the distribution of y. Or if everything is discrete, it's a sum over y. That is, if the distribution of y is discrete, it's the sum over y instead of the integral over y. In either case, you have something that's called the law of total probability. Basically, you take the probability that x is in A and you split, and it's split up over all the possible values of y, and then we integrate it out and get an average, which is the overall unconditional probability. We'll use this tool. And now here's the zipper example. Members of a senior kindergarten class, which we'll treat as a sample, try to zip their coats within 1 minute. We observe whether or not each child succeeds. How about a model? Well, before we do pick a model, you see that this is a lot like the coffee example, and succeeding at zipping your coat is a lot like picking the new brand of coffee. And accordingly, the standard thing to do would be to assume that y1 through yn are independent and identically distributed Bernoulli random variables, where theta is the probability of success, and we're exactly in the same situation that we were in before with the coffee taste test. But do you actually like this model? Is this reasonable for little children zipping their coats? Here's a better one. Obviously, and here's why we need a better one. Obviously, the probability of success is not the same for every child. This is not like flipping the same coin over and over again and observing whether or not we got ahead. It's a different coin for every kid. Some children are better at zipping their coats than others, and some have coats that have easier zippers than others, and you don't expect them all to have the same probability of success. In fact, some children are almost certain to succeed, and others almost have no chance at all. So here's an alternative model. Let y1 through yn be independent random variables with yi still Bernoulli, but now the theta has got an I on it. There's a different probability of success for each kid in the sample. Don't you think that's reasonable? It might be true for the coffee too. Anyway, here we go. y1 through yn are independent Bernoulli with parameters 1 and theta I, and you can think of this now as a two-stage sampling model. The process of observing whether the succession of children can zip their coats or not is a two-stage sampling model. First, you sample from some population of children in which each child has a personal probability of success, call it theta I. Yeah, I know it's not really a random sample, but because it's probably just a kindergarten class, but we'll treat it as a random sample for our present purposes. This is about modeling, and this is what people do all the time with data that could be described as a convenience sample. They pretend, we pretend that it is a real random sample and go ahead and do nice technical things with it, even though it's pretty hard to justify. We'll have to return to this point later, because right now we're going to be living in the world of the technical model for a little while. But we should come back to this. We'll come back to the fact that our samples are usually not really random samples. So, to restart this point, it's a two-stage sampling plan. It's a two-stage sampling model, and the first stage is to sample from a population of children and get a set of probabilities of success, and then independently for child I, we'll use, this is the second stage, use theta I to randomly generate success or failure. And that's the model. You have to notice here that theta 1 through theta n are random. They're not observable, of course. They're each child's own probability, which we really wish we knew. They're all random variables with some probability distribution. Who knows what it is? Whatever it is, it's, since they're probabilities, it must be supported on the interval from 0 to 1. I made it closed. You could argue about that if you wanted to. But yeah, let's make it a closed interval from 0 to 1. And leave the philosophic discussions for later. Well, what kind of distribution? How about a beta distribution? Yeah, here's the beta density. It's a nice conventional density on the interval from 0 to 1. And this is not quite like buying your clothes from Walmart, because it's pretty flexible. Here's an example. So let me go back. The parameters are alpha and beta. And alpha is greater than 0 and beta is greater than 0. And the main thing that we remember about the beta density is that it's, first of all, that if alpha equals beta equals 1, then it's uniform on the interval from 0 to 1. And I guess one other thing is that the expected value of a beta is alpha over alpha plus beta, which in case alpha and beta were equal to 1 would be 1 over 1 plus 1 are a half, which is indeed the expected value of a uniform. But depending upon the values of alpha and beta, this distribution can assume a variety of different shapes. Here's one with alpha equals 2 and beta equals 4, so that the expected value is around a third. If we reverse those, alpha equals 4 and beta equals 2, we'll get a hump over on the other side. Alpha equals 3 and beta equals 3 gives you a nice symmetric one around the half. And if you let the alpha and beta be less than 1, then you can even get a U-shaped density for the beta, or something like this, or and many other shapes, but not multimodal. Well, except to the extent that these U-shapes are bimodal, because they've got a mode at each end. Still, it's a lot of different shapes. How about that as a first try for an unknown probability distribution of the probability, a probability distribution of the probability of being able to zip your coat. So we'll apply the law of total probability, which is why we did this in the first place, and double expectation as follows. To get the probability that a kid will be able to zip her coat is going to just be the integral from 0 to 1 of the probability that you could do it given theta. That's right. Yeah, that's right. So this is the I guess y here is playing the role of x in our earlier discussions, and theta is playing the role of y. Yeah. So this is the probability that y equals 1 is the conditioning out theta is the well, it's really the expected value of the probability that yi equals 1, and that's just, what is the probability that yi equals 1 given theta? It's just theta itself. So by the way, we'll get back to this point later, but this is the expected value of theta. This is the expected value of that unknown distribution. And in the case of a beta, we can write it this way. And by a little trick or so, it's pretty easy to do this integral in spite of the gamma function sitting there, and get alpha over alpha plus beta as the answer, which is the expected value of beta. That's this expected value. So we've got the probability that yi equals 1, and that means that we can look at the distribution of the observable data. Now, then that is the probability that the random vector y, which is actually boldface y, y1 through yn, assumes the little value y, which is little y1 through little y, and given alpha and beta, is, well, it's the product, because they're all independent, right, of a bunch of Bernoullis. There they are. Alpha plus beta, right? Because this alpha over alpha plus beta, that's the probability that yi equals 1. So it's good. It's like a theta. But there's a little problem here. And that's that the distribution of the observable data that we've got up here, by the way, this is the likelihood too, right? The distribution of the observable data depends on the parameters alpha and beta only through the function alpha over alpha plus beta. And for any set of yi values, there's infinitely many alpha beta pairs that then give exactly the same distribution of the data. Infinitely many. Any set, any pair alpha beta satisfying that alpha over alpha plus beta equals a constant is going to give you exactly the same probability distribution. And so how could you use the data to decide which one of those probability distribution, which one of those pairs, which one of those alpha beta pairs is the right one? This is a general problem. It's called parameter identifiability. The parameters of the zipper model are not identifiable, which means that you can't recover those parameters from the distribution of the sample data. That's the real meaning of the idea of identifiability, is a kind of a recoverability or knowability. The model parameters can't be recovered from the distribution of the sample data, not uniquely. All you can ever learn from sample data is the distribution from which it comes. You won't even learn that exactly, but as the sample size gets bigger and bigger, you get closer and closer to learning what the distribution of the data is. But if the distribution, even if you knew it perfectly, can't tell you what the parameters are, then how can the sample data give you even an acceptable version of an acceptable guess at what the parameters are? So anyway, in this circumstance, there's going to be problems using the sample data for estimation and inference about the parameters. And this is true even if the model is completely correct. I submit to you that the zipper example, the model that we've got, where each child has their own probability of success, is a much more reasonable model than the usual Bernoulli model, but unfortunately, we cannot estimate the parameters of the model successfully. Here are some definitions that are connected to parameter identifiability. Again, a statistical model is just a set of assertions that partly specify the probability distribution of the observable data. Suppose that a statistical model implies that a data vector D is distributed this way, as P sub theta, where theta is some parameter vector, see I made it boldface, some parameter vector that sits in a parameter space. If no 2 points in the parameter space in cap theta yield the same probability distribution, oh, that's right, see, right? Then the parameter theta is said to be identifiable. Okay, notice how when our sample data depended upon the parameter vector alpha comma beta only through the function alpha over alpha plus beta, then alpha equals beta equals 1, which gave you a ratio of a half, is also the same as will give you the same probability distribution of yi as alpha equals beta equals 10. Also, 10 over 20, also a half. Even though the picture of the of that probability of success is very different for alpha equals beta equals 1, where it's uniform, and alpha equals beta equals 10, where it's centered on a half but very, very skinny and narrow with small variance. So you see that this definition excludes the case that we were considering. That is, identifiability means that if two parameters are different, that must mean that their probability distributions are different. That is, the probabilities they give must be different for some set anyway. Even though they might be quite similar, there's some difference in the probability distributions. On the other hand, if there are two distinct theta 1 and theta 2 in a parameter space with exactly the same probability distribution, we'll say that the parameter theta is not identifiable. And another way of it's an equivalent definition, and it's another way of looking at it is that the probability distribution of the data is always a function of the parameter vector. And if that function is 1 to 1, then the parameter vector is identifiable. That is, that you would then be able to recover the probability distribution of the data from the parameter. Anyway, the function is 1 to 1 because then theta 1 not equal to theta 2 giving the same distribution couldn't happen if the function is 1 to 1. And so if the parameter vector can somehow be recovered, from the distribution of the data, then it's identifiable. This is another way of thinking about it that's handy. Here's a big theorem about identifiability, which is that if the parameter vector is not identifiable, then consistent estimation for all points in the parameter space is not possible. I am getting ahead of myself just a little bit. I would be nice if you knew what consistent estimation is from some other course, but consistent estimation is a large sample property of a statistical estimator, which says that if you take a tiny little interval or region around the true parameter value, and you look at what happens to the probability distribution of the estimator as the sample size approaches infinity, then as the sample size approaches infinity, more and more and more of the probability distribution of the estimator gets concentrated in a little neighborhood around the true parameter value. Essentially, it means that you will, with high probability, be very close to the right answer if you get your sample size large enough, because typically these little neighborhoods are supposed to be epsilon neighborhoods and kind of small. So you can see again that we need to talk about large sample theory. Maybe I should have done it first, but I didn't. And here's the situation now. Remember that the key is that the probability distribution of the estimator gets concentrated into a little neighborhood around the true parameter value. But in this case, theta 1 and theta 2 are two different parameter values, which, however, give rise to exactly the same probability distribution of the sample data. And here's a little neighborhood around theta 1, and here's a little neighborhood around theta 2. And the so this is the idea. Suppose theta 1 is not equal to theta 2, but the two distributions of the sample data are the same. That would be true for any n. Then the estimator Tn, which is a function of the data, must suppose that the estimator converges in probability to the true parameter theta for all theta in a parameter space. Again, convergence in probability means that the probability distribution is getting concentrated around the true value. In that case, you see, the problem is that suppose that theta 1 were the true parameter value. That means that more and more of the probability would have to get concentrated in this little neighborhood. But since the probability distribution of the estimator is identical for theta 1 and theta 2, it means also that the probability is also going to have to get concentrated in here. And after a while, this one has to get bigger than a half, and this one has to get bigger than a half, and it's impossible. And that's really the key of the epsilon delta type proof, that if you have the parameter not identifiable, consistent estimation for all points in the parameter space is impossible. which means that it's a failure. It's a failure as the sample size goes to infinity, which is when you would hope that you would get the truth. Why don't you hear more about identifiability? It seems like a foundational critical issue, and it really is. But if you've proved consistent estimation, then you've indirectly proved identifiability, because identifiability would be impossible. Without identifiability, then the consistent estimation would be impossible. So if you got consistent estimation, the parameter must be identifiable. So people often just talk about consistency. Also, I should mention that any function, sometimes the whole parameter vector isn't identifiable, but a function of it could be estimated consistently. And in that case, that function of the parameter vector is identifiable. Here's what happens. Now what we're going to do is we're going to, oh, you know what? Let me go back. Here's an example of a function of the parameter vector that's estimable. Alpha over alpha plus beta, for the beta example. Alpha and beta together as a vector are not identifiable. However, since the probability yi equals 1 is alpha over alpha plus beta, and that's just the probability that yi equals 1, then that function can be estimated by a sample mean. Consistency of the sample mean. Again, we need to talk about large sample theory. A direct application of maximum likelihood has got to fail for the zipper example, and here's how it goes. Here's the likelihood function. Yeah, you know, there it is. You've taken the product from I equals 1 to n of the likelihood function, and we've done a little simplification and gotten this alpha over alpha plus beta to the sum of y, and 1 minus this quantity that would be like a theta to n minus yi. And then, you know, we take take the log of it, and then you simplify it a little bit more, and you partially differentiate with respect to alpha and beta, set both equations to 0 and solve, because that's how you would do a maximum likelihood problem for that's how you would do maximum likelihood for a multi-parameter problem. You get two equations and two unknowns. First, we differentiate the log likelihood with respect to alpha and set that to 0, and when you do, you get alpha over alpha plus beta equals y bar. Okay, good. It works very much like the other maximum likelihood example that I showed you in the first slide set. The second one is you differentiate the log likelihood with respect to beta and set that to 0, and the result is, again, alpha over alpha plus beta equals y bar. So you've got two equations and two unknowns, but unfortunately those two equations are identical. And any pair, alpha beta, with alpha over alpha plus beta equals y bar will maximize the likelihood. That is, the maximum likelihood estimate is not unique. There's infinitely many of them. Geometrically, what do we have? Alpha over alpha plus beta equals y bar. I'll solve for beta and get that beta is equal to 1 minus y bar over y bar, that quantity times alpha, and that's the equation of a line, right? And the slope is 1 minus y bar over y bar. And it looks like this. So every point along this line, assuming that the slope is y bar over 1 minus, is 1 minus y bar over y bar. Every point on this line is a maximum of the likelihood function, and the likelihood function itself will look sort of like a sheet draped over a clothesline, and there's a ridge along the top where the maximum occurs, and it just occurs, it's the same height at all these points that satisfy this alpha over alpha plus beta equals y bar. A non-unique answer. There are infinitely many pairs, alpha and beta, which are equally consistent with the sample data, and estimation has failed by the most mainstream and robust technique that we've got, given that we have a parametric model. Look what's happened to us. We made an honest attempt to come up with a better model, and it was a better model, but the result was a disaster. There is some good news. by the law of total probability, the probability that yi equals 1 is the is this integral of theta I times f of theta I, and that is the expected value of theta I. Oh, I maybe not doing notation very well here. This, I made this a capital theta because it's a random variable, and I've been using the capital theta for the parameter space. So anyway, this capital theta is a parameter. That anyway, it's the expected value of the probability of success. It's the average probability of success in the population. So that even when the probability distribution of the probability of success is completely unknown, not just beta, but any old distribution supported on 0 to 1, you can estimate its expected value with whatever you want to call it mu, consistently. That is, so that we have convergence in probability to the right answer with y bar. The consistency of a sample mean as an estimator of an expected value is something that we have to cover in the large sample theory module that's coming up next. Anyway, that function of the unknown probability distribution, not just alpha and beta, it's this expected value, which I've called mu here, is a function of alpha and beta if the distribution of the probability of success is beta. But if it's some other unknown distribution, who knows what it is, but still that expected value is a function of the unknown probability distribution, and that function is identifiable. And often that's all we really care about anyway. Mostly what we care about, say for comparing group means under different treatments, you might not be that interested. Well, of course you would like to know exactly what the probability distribution of ability is, but if you could recover average ability, that's a gain. And for many purposes, it would be all that we would really need to know. Which means that, you know what that comes back to, though, is that the usual procedures based on the first thought about these binary data, which is that they should be Bernoulli, right, with a flip of a biased coin, and we're trying to make an inference about what that probability of a head is, which is such a bad model for children zipping their zippers. But still, if you went through the drill and made inferences about this expected value of theta using a Bernoulli model, you'd come to a reasonable answer. You'd be able to make inference not about that common probability of success, which there isn't any, but about the average probability of success, which is something that makes sense. And anyway, the usual procedures are actually informative about a much more realistic model, that is one where everybody's got their own probability of success, whose parameter vector is not fully identifiable. And we don't often get this lucky. But still, it's indirectly, if nothing else, it's a good justification of the usual seemingly sloppy way of adopting a Bernoulli model for binary data. It justifies adopting that Bernoulli model for the coffee example too. Surely everybody has got a different taste, and so everybody's got a different probability of choosing the new coffee as the preferred one. Because, by the way, there is uncertainty when people make choices like which one is better. Sometimes they get it mixed up, sometimes they're not sure. So there's a probability, there's a second stage probability process going on with people making choices, even if they have their own probability. They have their own individual probability of choosing the coffee or zipping the coat or anything. So this whole discussion, first of all, it introduces the issue of parameter identifiability, and we'll definitely get back to it because it's very big in regression, even though it doesn't get much airtime. And at the same time, it justifies a standard procedure in in an indirect way that you wouldn't anticipate. One more question about the parametric version, that is where you have a beta distribution for the probability of success. What would it take to estimate alpha and beta successfully? Because we can't do it with the usual data set. Try this. Get the children to try zipping their coats twice, maybe on 2 consecutive days. Assume that their ability doesn't change. I guess that's right. And also that conditionally on their ability, the 2 tries are independent. And if you are able to live with those assumptions, that'll do it. And you would be able to estimate alpha and beta separately. Writing down the model is an interesting challenge and may appear as a homework problem in the future. Anyway, this is the kind of thing that often happens. Sometimes the parameters of a reasonable model are not identifiable, but it's possible to design a different way of collecting the data so that the parameters can be identified. The moral of the story is that if you think up a better model for standard kinds of data, the parameters of the model you come up with may not be identifiable, and you need to check. And if you're uncertain about, if you're sitting in an academic talk in statistics and you're not certain what to say, but you want to say something that sounds pretty good, after the person has introduced a statistical model that you can barely follow, and has started perhaps to talk about estimation, you say, well, what about identifiability? And then they have to answer you, and it's sometimes they don't know. Of course, if they've proved consistency, you're okay. Anyway, if you do come up with a different kind of model, the parameters might be identifiable, and you need to check. And if there's a problem, it's not necessarily with the model. The model might be okay. The problem is with the data, that the data are not capable of casting full light on the model parameters. And the solution is better research design. So this is the connection between parameter identifiability, which is the knowability of the things that you really want to know, and the actual design of the study. You know, maybe collecting the data twice independently instead of just once. But sometimes when you think about things like this and come up with another research design, you'll find that this is not a common way to collect the data at all. And if data have already been collected, they probably haven't done it in a way that will allow you to identify the parameters of your model. So you have to be in on the ground floor to, if you possibly can. And, yep, there it is, the end. It was an open source document.